So now we're going to talk about exercise 2.23, which is related to problem 2.4. And I've covered problem 2.4 in a previous video. So I linked the video below in the description. So be sure to check it out if you haven't yet done so. So in problem 2.4, we had this book on a wall. And between the book and the wall, there was a coefficient of friction, mu. And we're applying a force, F, upwards to the right to keep this book up. And there was also this friction pointing upwards. And it was basically asking us what's the minimum force to keep this book up. And our exercise 2.23 is asking us for the maximum allowable force. So let's think about it. What happens when capital F gets really, really big? Well, friction won't point upwards anymore, because previously when our F is at minimum value, we needed friction to help us from stopping the book from dropping down. But now because our F, the applied force, capital F, is so large, that the book now has a tendency to move up, and so friction must point downwards to oppose that tendency. So then now let's try to list our equations. So horizontally, the equation is still the same, because friction doesn't have a horizontal component. So for vertical components, we have F sine theta equals to F plus G. And then F is still smaller or equals to mu n. And so let's try to isolate F, friction, from this formula, from the second formula. So F needs to be F sine theta minus G, which is F sine theta, minus mg, if we let the book mass be m. And then we know that n is equal to F cosine theta. So then we know that F sine theta minus mg needs to be smaller or equals to mu F cosine theta. And then let's try to isolate F. So F sine theta minus mu F cosine theta needs to be smaller or equals to mg. And so F, we bring the F out, F sine theta minus mu cosine theta needs to be smaller or equals to mg. So then F needs to be smaller or equals to mg sine theta minus mu cosine theta. And so that is our upper bound, the maximum allowable force. So now we have the formula for the upper bound for F. And the question also asks us for a special angle that arises. So that is when sine theta minus mu cosine theta equals to 0, because this will make F blow up, and there will exist no force that can keep this book up. So then we have, let's divide by cosine theta here. So tangent theta minus mu equals to 0, and then we know that tangent theta equals to positive mu. Theta needs to be inverse tangent mu, and so that is the special angle. And that is really similar to what we found in the previous problem, which was negative mu here. And so now, to put it in proper notation, we have F needs to be smaller or equals to mg over sine theta minus mu cosine theta, and it needs to be bigger or equals to mg mu cosine theta plus sine theta. And so now we can try to graph this on decimals. It is also asking us for a rough plot. So here we have the graph. So this is the upper bound. So I used u for mu, x as theta, and then m and g. So then m and g, u are all arbitrary constants, and we can adjust their values, but they really wouldn't change the overall shape. So if we look here, I've grayed out the areas that are not included in the boundary. So it was 2 over pi to pi over 2 to negative pi over 2, and any values outside of that is not considered, and that's why I've graded out. So then the purple line here is the upper bound, and the red line here is the lower bound. Let me drag the graph down a bit so we can see a bit clearly. So the area between the purple line and the red line is the allowable force.